Rates of change. Objectives. By the end of this lesson, you should be able to recognize all notation of the derivative function. Actually, that one's wrong. It'll be next video. Set up the limit needed to find a derivative function, a derivative of f of x. That one's true. That's definitely one of the objectives, along with how to find slope of a tangent line. That's kind of the goal for this lesson. So let's talk about rate of change. Right, rate comparison between two quantities of units. You guys have been doing this since algebra 1. Right, so here's some examples of rates. Sir Thomas Bradman's average batting rate at test cricket level. That's totally an IB universe. Who knows what cricket is? Michael Jordan's average basketball scoring rate was 20. Okay, that's wrong. It's like 30 points per game, but whatever. But right, a rate is so scoring per game, right? Score points per game. Randy's average typing rate is 60 words per minute, right? Notice how 99.94 runs. That's a lot of runs. Cricket's weird. Runs per inning, right? It's that per thing, right? That lets you know it's a rate. This per that. The most common rate you guys are all used to is speed, right? Common use rate, speed. Distance per unit time. So right, rate is distance divided by time. In general, the whole idea here is rate. Is this a slope between 2 points? Right? If you have, it takes an hour to travel this direction, and it takes you, and you've gone up 60 kilometers, right? How do you find out your rate of this? It's rise over run, right? Slope, right? 60 kilometers per 1 hour. So rate is just slope, right? You find 2 points. You want to find the rate between those 2 points. You do the slope equation. So that's what rate is. Now a little more detailed. What if I want the instantaneous rate to change? So what does that mean? It wants that wants the slope at a single point. That's kind of weird, right? The slope equation is this: y2 minus y1 over x2 minus x1. When you start getting calculus, they start changing y1 for f of x1, which is the same thing. They'll start changing y2 for f of x2. Right? It's the same equation though. Right? But that's how you find slope. It's right. You need 2 points to find the slope. So how do you find the slope of 1 point? Well, that's what a lot of this lesson's about. So we call that the instantaneous rate of change, right? So it's a rate of change at that one moment. So it's kind of saying if we're talking about speed, how fast are you going at that one moment? Right? How many points per game is he scoring? How many points is he scoring in that one game? How many cricket points you score in a game of cricket? I guess I gotta watch some cricket games. So this rate of change depends on the variable represent independent variable, blah blah blah, blah 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 blah. Right? All it's just saying is that if we're talking about speed, that's probably the easiest way to measure it, is how fast you're going at that one moment. Right? If I erase some of this, you could see a little better, because I roll over it. That was not the erase button. Here we go. Right? Notice how over here you have 2 points you're crossing through. Right? It starts right here, and it goes through there. Right? That's a slope. This only has 1 point it hits, right? Right there. 2 points, we call that a secant line. We'll talk about that more in a second. Secant line. Good old geometry. If you go through 1 point, we're going to call that a tangent line. So instantaneous rate of change is also known as the slope of a tan line. So how do we find that slope of that tan line? Well, that's what we're talking about next. First, a little more background. Here are the inventors of calculus: Isaac Newton and Gottfried Leibniz. Newton is the one that's most famous for doing it, because he technically did it first. He didn't publish his articles for like 5 years until Leibniz did. But they both created independently. We actually use a lot more Leibniz's notation than we do Newton's, but Newton is known as the father of calculus. There's a whole like gritty backstory behind them and how they fought and all that stuff. But that's not for this class. Now let's talk more about what we are talking about. the best way to describe what we're learning about, which is the study of rates and change, is here's my roller coaster. Right, calculus is generally the study of rates of change. So what I was talking about earlier, let's say here's your roller coaster on this point. You want to see how fast it gets from that point to this point, like on average, how fast is it going? Right? So if you want to find the rate of change, right, from those 2 points, like, oh, how fast is that roller coaster traveling from there to there? Right? What we always do, right? We find the slope. So you draw a line between these, draw a line. You guys understand the trouble of drawing a line on this thing is. So we're gonna draw a line between these 2 points. I could do it. I could do it. Close enough. Right, so you draw a line between those 2 points and you find a slope. y2 minus y1 over x2 minus x1. Right? General slope, that's an awful, awful line. I know. Sorry. Right? But that's the rate of change. Right? You want to find how fast on average is that thing going from there to there. Draw a line between the 2 points, find the slope, y2 minus y1 over x2 minus x1. So that's normal rate of change. So what does instantaneous rate of change mean? Well, instantaneous rate of change means how fast you're going at the exact moment. So if I want the instantaneous rate of change, let's say right here. Instantaneous rate of change means what's your speed at that one moment? How fast are you going at that moment? Right, where average rate of change tells you on average what the speed is. Oh, what's the average speed? Like when you talk about roller coaster, what's the average speed of the whole ride? Right, like that's the rate of change you can find. Super simple, just find the slope. Instantaneous rate of change tells you what's the speed at that exact moment. Right, like the max speed of this ride is something. Right. So if we want to find instantaneous rate of change, we gotta find the slope of that point right there. Right. Remember we talked about this? Like, how do you find the slope of one point? Well, you have to draw a little tangent line there. This is the worst thing in the world. There you go. That's a line that's kind of hits a tangent line. Right? But how do you find the slope of a tangent line? Right? This is where calculus comes in. So I'll give you the general idea behind it, but then we'll talk about it more in a second. But the general idea is you can't find the slope of 1 point without calculus. What you do is you find the slope of 2 points. Also works much better if we draw a straight line. Hey, not bad. Right? So that's the slope of 2 points. Find that. You can do that. Psh. Then you can find the slope of, how about you get a little closer? Find the slope of these 2 points. Right? And let's just do an example. Let's say the slope of this first point was like 6. Negative 6 going down. And slope of this point was like negative 5.5. Let's get a little closer. Let's say that one was like negative 5.2. I know how awful it is going to tell me. Then you get a little closer. And so that one's negative 5.2, 5.15. And then you get a little closer. I realize, guys, it looks like Medusa's head or something right there, but I'm trying. Look at what I'm thinking, not what I'm writing, because it's awful. Right, 5.13. Right, let's get a little closer. That's negative 5.1. So, right, I start off with that, and then I got a little closer, I got that. I got a little closer, I got that. I got a little closer, and I got this. I got a little closer, and I got this. Right, if you look at it, if I keep on getting closer and closer, doesn't it look like I can't even make that a straight line. Doesn't it look like it's gonna get close to negative 5? You know what that is? That's the limit. Right, so we take the limit of all the slopes of secant lines. It equals the slope of a tan line. And that's how you find the slope of a tan line. You take the slope of all the little secant lines, and then you take the limit of all the slope of the secant lines, and then you get a tan line. That's the way it's going to work. Right? So as I got closer and closer and closer, it got closer and closer to -5. So that's going to be the slope of the tan line. Let's show you with a better picture in a second after I do this. Right? So first, so here's the secant line. You can kind of see that blue line. I would highlight it, but then you just make fun of my line again, so I'm not going to. But you can see in blue right there. In blue right there. Right? So that's the secant line. You want to find the slope of that thing? Right? Slope's going to equal, right, y2 minus y1, so f of x minus f of a over x2 minus x1. Right? This is normal slope. Don't worry about x minus a, sorry. Right? Don't worry about that stuff. That's just normal slope equation. So that's the secant line. A tangent line hits it at one spot. Right? That's a tangent line. Hit at one spot. So how do we find the slope of that tangent line? Just like I was trying to demonstrate earlier. Right? You find the slope of the secant line right there. Look at that blue line. Then you get a little bit closer. And a little bit closer. And if you do enough times, you can take the limit of it. And that will give the slope of the tan line. Right? So the general idea here, guys, is if you take the limit of the secant lines, slope of the secant lines, it equals the slope of the tan line. So let's talk about that more. Let's get that more in detail. So we're in derivative calculus, differential calculus, right? It's one of the two. There's like two big branches of calculus we're going to talk about: differential calculus and integral calculus. So first things first, what the heck is a derivative? I kind of alluded to it. But when I say derivative, we're talking about three things. The one I've been talking about right now is right. The ones you heard so far is instantaneous rate of change, which means how fast you're going at that one point. Also, slope of a tan line. Right, those are two big ones I want you to know for this class. Limit of difference quotient, that'll make more sense if you ever take calculus or AP calculus. But really for this class, when I say derivative, I want you to know two things. That it's an instantaneous rate of change, so how fast is the thing going at that one moment, or how fast is the thing changing at that one moment. It doesn't have to be speed, it could be anything. And it's also slope of a tan line. Oh, and I realize, I hope if you actually see the words. I'm working on it. All right, but those two things. Those are two things I really want you to focus on with what derivative is. It's how fast something's changing at a specific moment. It's instantaneous rate of change. And it's the slope of a tan line. That's what derivative is. So if I say what's a derivative, you go, okay, it's the slope of a tan line or it's instantaneous rate of change. A lot of times you'll see this for your derivative. So when I want the derivative, I'll write a little an f dash x. So you'll see me write the derivative. Or I might write dy dx, and we'll talk more about that in the next video. Or I might write y prime. We'll go over more and more of those. But in general, if you see that notation, that means what's a derivative. So you're thinking, what's the slope of the tan line there? That's what that means. And let's do that. Let's do our first example. Now they should have f of 4 value. They should tell you what f of 4 is, but they don't give you the y values here. So I'll just do it. Here's 1, here's 2, 3, here's 4. Right? So look at the first one. They want to know what f of 4 is. Well, it's simple. Right? F of 4, here's 4, go to the point, 2. Done. The next question is, what's f prime of 4? Right, little dash. Now remember, what does that mean? It means instantaneous rate of change, or in this context, slope of the tan line. So this is how we're going to find it. Right? So here's my graph. See how this thing hits it at one spot? That's a tan line. You guys might laugh. I'm very proud of that line right there. So let's find the slope of that tan line. We know how to do it. y2 minus y1. It's like if I slope of any line. x2 minus x1. So next. I have 2 points. I have 6, 4. That's x1, y1. And I have this right here. 0, 2. 2, 0. 2, 0. I can even use, if I wanted to, 4, 2. Right, so plug it in. This will be x2, y2. So plug it in. So y2 is 0, y1 is 4, x2 is 2, and x1 is 6. I get -4 over -4, or just 1. That's the slope of that. That's the derivative. We just took our first derivative. Very proud of you guys. Right? All it is slope of the tan line. That's all it is. If I say, what's the derivative of this? You could draw the function, draw the tan line at that point, and find the slope of it. Right? So that's the derivative at 4. Now notice, before I move on, what if I wanted a derivative at -4? Now we're not actually going to find it, but let's talk about it. Here's -4. Here's my graph. If I draw a tan line for this thing, it's going to be very hard to do. That's the closest you're going to get, right? I want you to notice something about that graph. What do you notice about that slope compared to this slope? Well, if you look at this one's going up, so this slope is positive. This slope is negative. It's going down. The slope changes, guys, with where you're going. The slope right here will be a little higher bigger than the slope right here. The slope right there will be a little bigger than the slope right there. The slope right here is being different than those slopes, right? So the slope of the tan line, the derivative changes as you go. It all kind of depends on where your graph's at. So let's talk about that more in detail right here. This is an example, right? So for this graph here, we're going to find f of all these values, and then we're going to find a derivative at all those values also. Let's do the easy ones first, right? F of -2. Well, here's -2. F is just that value right there. So, looks like that's 0. Now I want f prime at -2. That's the slope of the tangent line at -2. Sorry, right here. Now here's the thing with the straight line. If you have a straight line, the tangent line is the exact same line. Because look, try to hit it at one spot. It's the same thing. Now that does not mean the answer is 0. Because remember, this means slope of the tan line. So I got to find the slope of this line right here. So easy way to do it. Pick 2 points. This looks like it's -4 and -2. I'll pick this point right here, which is like -2 and 0. You can do the slope equation. I'm just going to do rise over run. I went over 2 and I went up 2. So slope is 1. Again, notice, right? F of -2 is like, what's the value at -2? Right there, it's on the x-axis, so 0. F prime means what's the slope of the tan line. So I draw a tan line at that spot. When it's a straight line, it's the exact same line. Then find the slope of that, right? Derivative means slope of the tan line. Now let's go f of 1. F of 1's right here. There's really no value. Let's just say it's 1. F prime of 1, right? Slope of the tan line. Now there's no so here's curve. I actually gotta draw a tan line. God, my tan lines are awful. So, and then you gotta find the slope of that tan line. I don't know, let's just estimate that, because come on, who cares? That's 2. Let's say that's 3. So my tan line is gonna be rise over run. So 3 over 2. Again, now it's an estimation. Anytime it's a curved line, it's just gonna be an estimation anyway. Let me erase this so we could see the next one. Just a little bit. I need to erase all of it. There you go. My erase game is strong, at least. So f of 2. So here's f of 2. Remember, when it's like that, you want the closed circle. So f of 2 right here is 4. F prime of 2. What's the slope of the tan line at 2? Look how it's all funky. You can't find it, right? Do I do it here? Do I draw it there? Also, if you can draw it there, how do I draw my tan line? I can go anywhere. You can't, guys. If it's discontinuous like this, you can't draw. You can't take a derivative of this thing right there. So, it does not exist. Yay, mean girls. She was lucky. F of 4. F of 4 is right there. Right, so the y value is this 3. And the next one, f prime 4, right? So what's the slope of the tan line at 4? So when you see prime, remember it's slope of tan line. So we go to 4. Now, remember, if you draw how you draw a tan line with a straight line, it's the line itself. And what's the slope of a horizontal line? 0. Remember, if it's a line like that, slope is 0. If a line's like this, slope is like no solution, no slope. So that's how you find slope. That's how you take a derivative when I give you a graph. If I give you a graph, I want to take the derivative, just draw tangent lines and find the slope of them. Because the derivative means slope of the tangent line. Okay, so now we know how to take the derivative of a graph, right? So if I give a derivative graph, slope of the tan line, no matter where I want it, just draw a tan line, find the slope of that tan line. Algebra 1 stuff. Okay, how about if I give you a function, right? No graph. So if I want to find a derivative, right? Instantaneous rate of change. So I want to know if I want the speed or the change of that one at that one moment, or if I want to find the slope of a tan line at that one spot. How do we do it with the function? Well, we use this formula right here. It's called the first principles. My box games is as good as my line game. So this is called the first principle. So if look at it, right? F prime of x equals the limit as h goes to 0, f of x plus h minus f of x all over h. So what that is, that's a fancy way of finding the slopes of the secant lines. That's all it is, right? Like I said, way up here, right? That you can see because my pictures are awful. If you draw lots of secant lines, you get closer and closer to a single point, and you take the limit of those lines, you're going to get the slope of a tan line. And that's what this thing's doing right here. It's just find the slope of, find the slope of all the tan lines, and we're taking the limit of that. Now, when we use this, using this is not that bad. You just kind of plug in the formula and do some algebra. The thing that people have a hard time with is this right here. F of x plus h. People freak the heck out with that. So let's do a couple practice ones right here. Let's say f of x equals 2x plus 3. I want to know what f of 1 is. Easy, right? 2 times 1 plus 3. Good, great, solid. F of triangle? We'll just plug triangle for x. 2 triangle plus 3. How about f of h? Well, let's plug in h for x. 2h plus 3. So how about f of x plus h? Right? Just like everything else, all you've been doing is plugging in for h. Do the exact same thing for x plus h, right? You plug x and h, x plus h, in for x there. So it should look like this. 2 parentheses x plus h plus 3. That's how you plug in x plus h. Don't freak out by the fact that it's x plus h. It works the same thing as anything else, right? All you do is plug in for the variable x. Right? Anywhere you see an x, plug in x plus h. So let's actually use this function. Let's actually do this, right? Let's find the derivative of this function here, x squared plus 1, using the definition of a derivative, the limit definition of a derivative. So this is the way this works. All right, so I'm gonna write down, okay. We're gonna do f prime of x. Now, the limit, let's write the limit down. Limit as h approaches 0. On the bottom, it's just h. That's just a variable. It could be x, it could be a, it could be w, it could be anything. They choose h, so it's h. Let's do this part. Let's talk about it. We just talked about it. Let's put it into action now. So here's my x. I'm going to plug in x plus h in for the x there. So this is going to be x plus h squared, right? All I did was plug that in for the x there. Don't forget the plus 1. That's still part of it. Plus 1. Right? So all I did was plug in x plus h for the x. There's still plus 1. And that's that part. Done. Minus f of x. So minus. Now, there's two very important parts that people mess up on. The first one is x plus h. People have a hard time with that. The second is minus f of x. They could do that. What's f of x? It's this thing. What they forget to do is to parentheses. Don't make me hate you. Make me want to kill small puppies. Put your parentheses. Right? So you plug in x squared plus 1. Right? That's what f of x is, but put your parentheses. If you forget that, you're going to be all wrong. That's the hard part of this. All we have to do now is simplify it. Okay. So we have to simplify x plus h. Okay, sorry. Before we simplify, remember we're doing a limit, right? So all the same limit rules apply. plug it in. Well, if you plug in, you get a 0 on the bottom already, so you know it's not going to work. You can plug a 0 there, it's just not going to work. Everything's going to kind of cancel out, right? So it doesn't work. You could try plugging 0, doesn't work, we got to fix it. So I shouldn't have skipped that step, but yeah. If you plug it in, it's not. I'll tell you right now, it's not going to work. So we got to simplify it first. So let's simplify this side. And again, don't do bad algebra. X plus h is not x squared plus h squared, right? It doesn't work that way. You actually got to multiply x plus h times x plus h. And when you do that, we distribute. We don't FOIL in my class. X squared plus xh. Same thing down here, plus xh plus h squared. You can add the middle 2 up. And you're going to get x squared plus 2xh plus h squared. Don't forget that plus 1's still there, right? Don't forget that's still there. We're going to distribute this negative into both of these. So negative x squared minus 1. Again, that's why it's so important to distribute with parentheses. All over h. Limit is h. 0. Now remember my goal here, guys, it's this normal limit. It's a limit problem. So what do I want to do? I want to be able to plug in 0. I can't do that right now because there's 0 on the bottom, there's 0 on top. It's going to mess everything up. So I'm trying to simplify it. So we expanded the top, we expanded the bottom. This is my favorite part, right? Now look at what happens. Hey, there's an x squared and a negative x squared. Those cancel. Hey, there's a plus 1 and minus 1. Those cancel. Look what you have left over. Limit as h approaches 0 of 2xh plus h squared all over h. Now remember, I want to plug in h. I want to plug in 0 for my h. I can't do it still. Hey, but what do you notice about the top? That's right, they will have an h. I can hear you. That's kind of creepy. I can't. So anyway, we get this, right? And now the h's cancel out, and I'm left with the limit as h approaches 0 of 2x plus h. And finally, now I can plug my 0 in. Now there's no issues, and I just get 2x. And that's the derivative of x squared plus 1. Derivative of x squared plus 1 is just 2x. What does that mean? Well, let's talk about it. Right? X squared plus 1 looks kind of like it's a parabola up 1. And this is saying that the derivative at any spot, if I take the derivative here, so that 10 line, take the derivative here, right? The slope of those lines right there is 2x. So if I want the slope of the 10 line at 4, you just got to plug in 4. So around like 8. Makes sense, like maybe 8. If I want at negative 2, I just got to plug in negative 2. And I'll get negative 4. Again, notice it's going down. Makes it plausible. Negative, going up. Positive, positive. Let's look at right here at 0. Well, look at the tan line there. It's a straight line. It should be 0. 2 times 0, 0. So that's all this is. This is an equation to find the slope of at any point of an x squared plus 1 graph, right? So the slope at any point of x squared plus 1 graph is 2x. You just got to plug the x value in. And that's the derivative. So that's our first derivative of a function. Let's do another one. Another 2 maybe. Just so. So this one, exact same. Let's just run it back, do it again. Right, notice how it says find dy dx. That's the exact same thing as saying f prime or y prime says take the derivative. So let me write down the formula so we can try this one. Limit as h approaches 0 of f of x plus h minus f of x all over h. Now again, sorry, it's the second one. We know how this, right? So if I want limit as h approaches 0, let's plug our stuff in, right? Now x plus h means plug in x plus h for the x's. I have 2 of them this time. Doesn't matter. X plus h squared plus minus 3 times x plus h. Right? That's all this part right there. Right? I plug x plus h into both of them. And now I gotta use the formula. Minus f of x. Now remember, we talked about we're gonna use parentheses. What's f of x? F of x is just this function right there. So x squared minus 3x. Right, parentheses. All over h. So What's next is what we always do. We simplify. So remember, this is probably the most annoying part because it's not x squared plus h. It is x plus h times x plus h. But once we do it enough, we know it's going to be x squared plus 2xh plus h squared. So let's just write this out. The limit as h approaches 0, that's going to be x squared plus 2xh plus h squared. Distribute this negative to both. Negative 3x minus 3h. Distribute this negative to both. Minus x squared plus 3x all over h. Again, my favorite part. Our whole goal here is, right, all that we're doing is like a fancy way of doing a limit, right? That's a derivative. We're trying to find the slope of all the secant lines. That's a fancy way of doing that. Right, our whole goal is to do a normal limit. I want to plug in 0 and get an answer. I couldn't do it at the very start because I have a 0 on the bottom and 0 on top. It's not going to work. I still can't do it here. But with a little luck, stuff cancels. This is so much fun. Right, so these cancel. Look at, there's a negative 3x and a positive 3x. General rule, anything without an h is going to cancel. But that's a general rule, if you do it correctly. So, we end up with that. So we have limit as h approaches 0 of 2xh plus h squared minus 3h all over h. Again, I still can't plug 0 in because of h on the bottom. If I plug it in, I'll have all h's on top. But we could factor. These all have an h, so you factor out the h out. 2x plus h minus 3 all over h, which is going to cancel out. And once they cancel out, right, all we're left with, I'll rewrite so you can see a little better. All we're left with is this, the limit as h approaches 0 of 2x plus h minus 3. Right, remember my whole goal is I want to plug that 0 in for h. That's the whole thing I wanted to do. So you plug it in, and we get 2x minus 3. So again, that's my derivative at any point. Right, so the derivatives of these things look like 2x minus 3. That's the whole idea. So we're going to quickly go over some things like right here. I'm not going to spend too much time on it. But the idea behind this stuff is the same idea, but now instead of just saying what's the derivative, they'll give you a point. They'll tell you what the a value is. Like, look at this. Probably best example is look here. Oh, use this, take the derivative of this, but use x equals 5. So we want x equals 5. Man, I cannot even circle things correctly. So I don't think I said that very well, but basically it's saying, right, let's take a derivative of this, and then I want what's the derivative at x equals 5. So there's actually two ways to do it. One way is just do what we've been doing, to do all that stuff, and then when you get here, just plug in 5. That's one way. Other ways to use this formula they have here, where instead of x, you plug in 5. That's the other way. I'll do one like that so you can see it, but it's not, honestly, I'll tell you right now, it's not my preferred way. My preferred way is to do what we've been doing, which we know how to do. Take the derivative, and then at the very end, plug in 5. But I'll try to do one real quick this way, because it's kind of obligated to. I signed an oath as a teacher. Well, I didn't sign one, but I made one up and then signed it. That's the idea. That's my personal problems. So, let's do this. So, if I want a derivative at 5, now again, look at the formula. I'm doing x squared plus 2x. So, this first part, right, just like I always, we're going to plug a plus h in for x. So, it's going to be squared. Now, it's a plus h. In this case, my a, the number I'm plugging in is 5. So, it's 5 plus h plus 2 times a plus h. But again, a, this case, is 5. I know, it's kind of weird. I've never been a fan of it either. Minus, using the formula, I'm done with this part, I'm at the formula part, parentheses, you promised me, f of 5. So I'm plug 5 into my formula here. All over h. Again, not my favorite way of doing it, but I did want to show you because it is sometimes they do sometimes. And then what we do here is this simplify like we're doing. Remember, the way you simplify plus h is don't be lazy. It's 5 plus h times 5 plus h. Distribute, you're going to get 25 plus 5h plus 5h plus h squared. So 10h by the middle too. I could distribute this. I'm going to get plus 10 plus 2h. And then distribute the negative here. and I get minus 25. I'll probably just add, let me add these two first actually. This is 25 plus 10, so 35. So it's going to be minus 35. All over h, the limit as h goes to 0. Now a couple things happen. If you look at this and this, let me simplify a little bit. I get 35 plus 10h plus h squared. I guess I get 12h because these two. Minus 35. I know it looks like a mess. I'm sorry. Well, the whole point is to say 35 and negative 35 cancel out, and you're left with 12h plus h squared all over the 12h. Limit as h goes to 0. I cannot plug in 0 yet, right? So you factor it. Gone. I have a limit as h approaches 0 of 12 plus h. Plug in the 0, and I get 12. And that's how you get the answer. Again, not my favorite way. I think that 5 plus h and that gets confusing. So generally what I just do is I take the limit this way because it actually makes a lot more sense to me with variables. I don't know why. Kind of weird. I've been told. I don't believe it. And then plug in the 5. That's the way I do it. So 36 minutes. I'm going to do some really fast. This is the last one I'm going to do. And I'll do it the way I talked about. Like, you could do it with a plus h. I think it makes it kind of funky. I always just like doing it the old-fashioned way, which is just literally do it limit. That says limit of f of x plus h minus f of x all over h. Right? And all I'm going to do is x plus h goes everywhere there's an x. So this is going to be the limit h approaches 0 of 5 minus 2 x plus h minus, not this part, 3 x plus h squared. That's all this part, right? Everywhere there's an x, plug in x plus h. That's the way it goes. Then there's a minus sign, parentheses, right? And then you can plug in f of x, which is this, all of this. So 5 minus 2x minus 3x squared all over h. That was a mic falling. That's how good I am sometimes. So then here we just simplify it, right? Distribute the 2, distribute the 3. Oh, actually got to do x plus h squared first, and cancel stuff out. Let me do that off camera a little bit. So I did a little math out off camera, so it's very some time. But right, distribute the 2 to both of them. Right, this you have to do x plus h squared times x plus h. So you multiply that, you get this. Distribute the negative 3, and you get this mess down here. Looks ugly, but remember what I said. If you do this correctly, anything without an h should kind of cancel out. 3x squared's gone. 2h, 2x, positive 2x, minus 2x. Negative 5, positive 5. Right, and all you're left with is this. 2h minus 6xh minus 3h squared all over h. You know what you could do there? Because again, the whole goal is to plug in the 0. That's my goal in life most of the time, honestly. But here, right, I can't plug it in, but I could factor out an h. So pull the h out, negative 2 minus 6x minus 3h all over h. Those cancel. Now I can take the limit as h approaches 0, because remember h on the bottom, that messes me up. And if you do that, right, you can plug 0 in. So let me rewrite it real quick. Negative 2 minus 6h minus 3h. 6x minus 3h. That's going to be 0, because you plug in 0 for h. That goes away. And your derivative is just negative 2 minus 6x. Right? I did all that stuff to get negative 2 minus 6x. Now, don't forget the last step of this. Last thing we're doing before I stop today. X equals negative 2. So what we do is just plug it in to our derivative. So negative 2 minus 6 times negative 2 is negative 2 plus 12, or just 10. I think that's the answer. Now again, what did we find? We found the slope of the tangent line of this equation at negative 2. The answer was 10. Right? If I graph that thing, it looks something like this. And that's saying at negative 2, slope is 10. Checks out. Right? That's how fast you're changing right there. That's the slope of the tangent line right there. All that good stuff. That's it.